So let's keep in mind that today is the deadline to complete your part 3 of test 1. Please make sure you do so. So let's all make sure we're going to complete our test 1 so we can move onward and upward towards the material that we're looking at now, which has to do with charge and matter still we're discussing. Now that we have, as I said last time, we have an idea of the way in which atoms are put together. And even though atoms are inherently neutral objects, but the reason they're neutral took a long time to discover that they were actually made up of individual positive and negative charges that with a little bit of effort can be separated. And then the interesting point about separating the charge on these materials is that now we can play all kinds of really cool games with electricity. So we're looking specifically at how charge distributes in matter and ultimately how that will lead to the electrical properties of things. So again, what I want to do is go to my slides so that we can take a look at the stuff that we're I want to actually back up a little bit on one of my slides because of what I had done. I realized I can't see too well, and I was looking right at what I was doing, and I didn't really say the right thing about what was on one of the slides, so I want to do that first after I hit the share button, and I'm going to come down here and get my PowerPoints up here, and I want to begin with a slide that we did on Wednesday of last week when we were talking about the qualitative vector summation of things that push in a direction as well as have a magnitude associated with them. And I gave this demonstration of a particular vector example, and I wasn't paying very careful attention to what I did. I'm showing this one at the very bottom of the page. So the top one, if you add an upward push of 8 newtons of force with an upward push of 12 newtons of force, people pushing in the same direction would act as if a single person is pushing with a net force of 20 newtons. Now, where I got myself in trouble was the one underneath that. I don't know what I was thinking when I was looking at it. I wasn't looking at it at all correctly. I have 4 individuals exerting force. I thought I had 3 individuals exerting force, and the 4th thing over was the resultant of the first 3 acting together. Here, let's say that I have 4 individuals pushing in the directions that you see, 2 pushing downward, 2, if you like, pulling kind of diagonally upward. The magnitude of the pushes downward are 20 and 30 newtons. And since they are acting together in the same direction, indicated by the angle at which the arrows that represent them are pointing, I can combine their efforts in the downward diagonal push to be 50 newtons. Then I have what's listed as F3 and F4 to the right of those. I wasn't looking at all correctly at this. I thought F4 was actually the answer to the combination of all the first 3. But in fact, what is happening is F3 and F4 are, if you like, pulling upwards diagonally in the same direction as indicated by their arrows that represent them. So the combination of action of F3 and F4 would be 50 newtons as well. But now they're diagonally upward to the left as opposed to F1 and F2 acting diagonally downward to the right. So the net result is the addition of the ones acting together and then the subtractions of the ones working in opposition. So what would happen if 4 individuals were pushing with these forces in these directions is that you would have a net force of 0. So essentially they're canceling one another out. And the object which they're applying these forces on would be sitting stationary because there's a balance between all their actions. Now, engineers actually have an interesting term for this. An engineer calls this a static situation. And if you're a civil engineer or an architect, a static situation is very important, meaning all the forces are acting equal and opposite of one another. So the net action of the forces is that they cancel. And you might say, well, who would want to do something like this? Well, believe me, if you're building a bridge and you're putting all those pieces of steel together to connect together to build this connection that takes you from one side of the river to the other, the connection of the beams in the bridge had better be a static situation, so that the sum of the forces of all the beams and girders and even the cement and all the other stuff pushing and pulling upon one another, so that there is no net force, so that the bridge is not accelerating. The bridge is sitting still. Same thing is true in any building you design or any structural entity that you make. Engineers are very concerned with static situations, meaning the sum of all forces is zero. Okay, now I'm going to skip the next couple slides because we talked about them on Wednesday. There's just some more examples of summing vectors. Here's another example of summing vectors together. Another one just for your entertainment. You should make sure you could do those, because on our little exercises I'm going to have planned for us for later this week that I'm going to post, then you will have your opportunity to do these things for me for your credit. And we began talking about Newton's gravitational force. And again, my motivation for doing this is because the electrical attractions between charges is eerily similar in flavor to the gravitational attraction between masses. So we began with the idea of gravitational attraction between masses because we have common everyday experience with gravity. We see it and are affected by it in our everyday lives. Now, we really don't see, at least overtly, the actions of positive and negative charge, attraction and repulsion. So I like to use the analogy of what happens with gravity as we discuss electrical attraction. Very, very similar in behavior. Now, as I mentioned to you last time, I am showing this formula. I'm even showing a couple numbers on this slide with regard to that formula, but I don't want you to panic. We are not here to do the hardcore things that you would do in several other layers of physics classes that you could take at higher levels than this one. If you want, and if you would have an interest in playing around with numbers with regard to these representation, the formulas that are representing these phenomena, I advise you to take one of the higher level physics classes where we certainly delve into those sorts of ideas. So essentially this magic formula for gravity, as we talked about last time, was F equals G, capital G, times M1 times M2 divided by R squared. And it says in the statement that the gravitational force of attraction that one mass exerts on another is directly proportional to their masses and inversely proportional to the square of the distance between them. And that's what the formula is showing. Directly proportional to the masses means if you double M1, you double F. If you double M2, you double F. When you put numbers into these formulas, that's what that's saying. And it's inversely proportional to the square of the distance. That's why there's an R squared in the denominator. And interestingly, if you double R, you cut the force by 1/4. Because if you double R, then you square it, you get a factor of 4 in the denominator, which makes the force 1/4 as big. If you put the objects 1/3 as far apart as they used to be, so they're a distance, say 3 feet apart, now you move them 1 foot apart. So you cut the distance between them by 1/3. What you'd have to do is put a factor in that denominator, 1/3 squared. And 1/3 squared is 1/9. So if you move them 1/3 of the distance they originally were, the gravitational pull they exert on each other is 9 times as big because of that factor of 1/3 in the denominator of this expression. That's what we call an inverse proportionality. Whatever you do to the R number, the inverse effect occurs on the F number because it's in the denominator of the expression. So that's how the numbers would work with regard to this. The most important number out of there is hidden behind my little blue sign. It's the gravitational proportionality constant, the universal gravitational constant, which is a very tiny number, 6.67 times 10 to the negative 11. Now, ultimately, what that means, as I talked about, and again, I'm kind of reviewing here, because the G number is so small, masses have to be huge before there's any appreciable or measurable gravitational force between objects. There's a definite gravitational attraction between you and I, but because our m's are of order of 10 to the 2, and because G is of order of 10 to the negative 11, there's not enough powers of 10 in our m's to make us have any gravitational force between us. But since the Earth has a gravitation or has an m of 10 to the 23, when you put that number into this formula, even if you put your small mass or my small mass, then that number of the mass of the Earth is so big that there's a huge gravitational force exerted between you and the Earth. All right, so again, I did this. I talked about Cavendish, the guy who figured out the G value. There's the magic number. He did a really clever experiment a long time ago with very heavy masses and put them on a mobile and had them pull on each other on the mobile and watch the mobile twist. And then he was able to figure out the magic number G by the amount of twist that the mobile took as it was attracted to a heavy mass. So then we talk a little bit about the idea of how object 1 and object 2 actually pull on one another. They pull on one another in a straight line between the two massive objects. Now there's again the magic formula, which we are not putting numbers in, but I want you to note that object 1 is attracted to object 2, and object 2 is attracted to object 1. That's why we have inward pulling arrows pointing on the straight line that connects object 1 to object 2. Now, as I mentioned as well, each exerts gravitational pull on one another. And I spent a great deal of time talking about that last Wednesday. If you didn't hear my lengthy discussion on that, maybe you should tune in to the posted lecture that I posted for last Wednesday. But let's now turn to the example of the Earth to the Moon. I posted right there in the upper, sort of the middle right side, the amount of force of attraction that the Moon and Earth exert on one another. Now, where does that magic number come from? Well, it's really not that hard to do if you have the formula from the previous slide. You know the mass of the Earth, which we do. You know the mass of the Moon, which we do. And you know the distance between the Earth and the Moon. You put all those numbers into that formula along with G, and you come up with this rather remarkable, huge number, 1.98 times 10 to the 20 newtons of force that the Earth and Moon exert on one another. Now, the attraction between them is equal and opposite. On the straight line connecting the Earth to the Moon, the Earth is pulled towards the Moon along that line. The Moon is pulled towards the Earth along that line. So, of course, we're all aware that the Moon goes around the Earth, not vice versa. And the reason behind that is if you now looked at the acceleration that this force causes, it's F equals ma. I'm sure we've all heard that magic formula, F equals ma, And again, we're really not here to do so much with the numbers. I just want to point out to you that the acceleration that the Earth would experience would be from the formula A equals F divided by M. So you have to divide that huge force number there by the mass of the Earth to find out how much the Earth is accelerated by the moon as being pulled by the moon. Well, the mass of the Earth is 10 to the 24. So you would divide this F, which is 10 to the 20, that's a big number, by an even bigger number. And what you would get for an acceleration of the Earth is a very tiny number. So the Earth is so massive compared to the moon that the Earth, even though there's a huge force between that the moon exerts on the Earth, there's not much acceleration that the Earth feels. The moon, on the other hand, is way lighter than the Earth. And the mass of moon that you divide by that same force would be an appreciable number. And that appreciable number will tell you how quickly the moon will be moving around the Earth. As a matter of fact, we have a rough idea. Every 30 days or so, we know that the moon goes through a cycle where it's come back around to the same point in its shadow that we cast upon each other. So it takes about 30 days for the moon to make a trip, not exactly, but roughly that many days for the moon to make a trip around the sun. I'm sorry, the moon to make a trip around the Earth. Now, I still will point out to you that this gravitational pull that the moon exerts is appreciable. How do we note it, and where can you note it? Well, you can note it by what is, of course, familiar to most people, the tide action on the Earth. The tide is the water level in the oceans that the Earth experiences, and it's solely due to the pull of the moon. The moon literally is yanking the water towards the shore when the moon is in a certain position as compared to when it is, now remember, this is partly due to the Earth spinning too. So the Earth is spinning around as the moon is moving. So when the Earth spins towards, the oceans on part of the Earth spin towards the moon, the water is yanked towards the moon and the water levels rise. As the Earth kind of moves the other direction, spinning, then the moon is further away and the tide levels fall because the moon is yanking the water kind of in the opposite direction on the planet Earth for that location. So the tides are directly tied to the motion of the and pull of the gravity of the moon onto the Earth. Now, another thing I just want everybody to recognize is that this force is uniform as the moon moves circularly around the Earth. They are pulling on each other equal and oppositely in each position where the moon is around the Earth. Now, this is what is known as Newton's third law of motion, which I have listed in red on the slide. For every action, there is equal and opposite reaction. This is a famous statement made by Isaac Newton himself. For every action, there is equal and opposite reaction. Now, here's the meaning of that. The gravitational force that I list on the middle right there, big number listed, is the same for the Earth pulled to the moon as it is for the moon pulled to the Earth. For every action, there is equal reaction. That's what that's saying. The Earth pulls the moon as hard as the moon pulls the Earth. It's more noticeable for the moon because the moon is lighter. Now, what is the other word? Very important word in there. Equal and opposite reaction. How to see the opposite idea, look at the arrows. The direction of push, or if you like, I prefer to use it, direction of pull that the moon exerts on the Earth is opposite to the direction of pull that the Earth exerts on the moon. Now they're equal in magnitude, opposite in direction. So this again is Newton's third law of action in the universe. If you want another example of it, I offered this last time. Turn around and push on something like the board behind you, And the harder you push on a stationary object, it feels to you, you have a sense that it is pushing back. And the harder you're pushing, the harder it pushes back. So for every action I supply, the wall seems to be pushing back equally hard against me. But it is not pushing in the direction I'm pushing, it is pushing in the opposite direction. That is another example of this Newton concept of action-reaction. Okay, so now what we're going to turn to in this long discussion on gravity, I think is kind of fun because it's something we deal with every day. But my motivation, again, for the entire discussion of gravity was to relate it to charge and the force that charge exerts on each other. To find that force, we will turn to this French dude. And this French dude was Charles Augustin Coulomb. He actually lived about 100 years after Newton, well, his period of activity, roughly 100 years after Newton, and roughly 100 years after Newton's idea of gravity, along came the Coulomb idea of electrostatic force. Now, first of all, let me indicate to you why we call it electrostatic. It is because, first of all, the first part of it, electro, says something about charge. And most importantly, it says something about electron charge. And that's where most of this is coming from. So all the charge we're going to be discussing is mostly going to be due to what happens with electrons. So that's the electro part of that word. What is the static part of that word? The word static, as we talked a little bit earlier here, means sitting still. So I have electrostatic force, and you often hear the term static electricity. Why do we always talk about static electricity as opposed to other kinds of electricity? Well, static electricity implies stationary electricity. This is a very important concept when it comes to charge. Why? Because there's competing things that occur when charge begins to move. When charge is static, the only attractions they can exert on one another is electrical. When charges are moving, they can still exert electrical pushes and pulls on one another, but a new phenomenon magically occurs. And that new phenomenon is one that we're going to spend some time on a little later. That is a magnetic phenomenon. Charge in motion is a magnet. So when we say electrostatic, we are isolating only plus and minus repulsion and attraction, keeping out of the picture magnetic attraction, North Pole and South Pole pulling of magnets. So again, this is a rather important distinction that I think we should have some concept of. Charge in motion always creates a magnet. That's what a magnet means. Magnets are charges moving. So when the charges are not moving, they are static, and then only their pluses and minuses can affect one another. So the French dude, Coulomb, started studying the force that charge A exerts on charge B. And he came up with this statement: two charged bodies exert an electrostatic force, meaning they're not moving, but they still attract each other with electricity of negative charge or repulsion of positive charges. They exert this charge upon one another directly proportional to their individual charge and inversely proportional to the square of the distance between them. This formula, ladies and gentlemen, is eerily similar to Newton's formula. Eerily. Now I'm using some different symbols. I use G in the Newton formula. We typically use K for the electrostatic constant, and we would replace that with a capital G for the gravitational constant. The R in the denominator is exactly the same. It's the square of the distance between two charges. And the numerator of the expression, again, replaces M1 and M2 with Q1 and Q2. Now, a couple things to say about the Q's. Q is what physicists like to use to represent charge. And there's a magnitude of charge or an amount of charge which you can deposit on a conductor of electricity. So the more charge you deposit, the bigger this Q number. The less charge you put on there, the smaller. So there's a magnitude associated with the amount of charge, and that is Q. Now, why is the Q are the Q's, and there are two charges? If they have attraction of charge 1 to charge 2, or attraction of charge 2 to charge 1. So we have a push or a pull that a charged object of value Q will exert on Q1, will exert on a charge Q2, and vice versa. So why then do we put the straight up and down lines on the formula? The straight up and down lines mean absolute value to mathematics. What does absolute value mean? Take the positive. Don't put a negative in. So the bottom line is charge can have a flavor of positive or negative. We talked about that before. What the brackets are saying, even if it's a negative charge, just throw the sign away. Just put the number in there. So when you multiply the K times the Q1 times the Q2 divided by the R squared, you're always guaranteed a positive number. There is no sign of force. That's a direction of force. The sign will kind of tell us the direction. So again, this formula is eerily similar. And I will show that on the next slide, to Newton's gravity equation. Finally, what I want to say is this with regard to it. We're not going to put the numbers in, just like I promised we're not putting numbers in the gravity equation. This is just demonstrating to you a couple things, mostly the fact that it's very similar looking to what gravity looks like. Okay, now then nextly, and I think this is again going to be hidden behind my sign here. There's my charges, there's my magnitude of force, there's the distance between them, and the K value is again a big number. It's 8.99 times 10 to the 9. 9 times 10 to the 9. It's again obscured by the blue button that says I'm recording. So I can't turn that off if you're looking at the slides. It's a big number. The value of K, the proportionality constant that turns the charge being interacting into a force that they feel, is big. So maybe the best thing to do is go to the next slide where I will summarize this. So K is, compared to G, is 10 to the 20 times larger. K has a magnitude of 10 to the 9. G has a magnitude of 10 to the minus 11. There's 20 powers of 10 difference between those numbers. What does that ultimately mean? There is a huge force with just little charge, but on the other hand, there's a small force with a relatively big mass in gravity. So because K is so much bigger than G, electric force is much stronger than gravity force, way stronger. And I think that we can maybe see it a little clearer here when I show the numbers on the next slide. Again, here's the formulas for the two phenomena. Again, we're not going to play with the formulas so much, but I'm showing you them side by side so you can see their eerie similarities with crazily different phenomena. Underneath them, I show the proportionality constants K and G. And once again, there's 20 powers of 10 different between the two. What does that mean? Tiny charges have appreciable forces between them. In gravity, you must be a huge mass before you have an appreciable attraction with mass. Now look, ladies and gentlemen, don't be surprised if you don't see a question like that. on my multiple guesses. Small charge can give big force because K is big. However, you have to have huge mass to have big gravity force because G is small. So ultimately, what does that mean? We have mass in our bodies, and are we held together by gravity force? No! You are not held together by the force of gravity. You are held together by the force of electrostatics. Why? Because you have a bunch of charges on all your atoms that make you up as well. And it's the attractions, even though those charges are tiny, there's substantial attraction between those charges. That's what holds you together. And the same thing is true with this wall behind me. All the matter in this wall is attracted to itself gravitationally. But the mass of the individual entities in the matter in the wall is so small that gravity is negligible. Of course, also the matter that makes up the wall is made up of charged stuff. And because the K value of the attraction to make the force out of those attractions is so big, the wall, the building, bridges, every structure that we construct has the rigidity that it exerts because of electrostatic attraction between the particles. Okay, so gravity is only important for very massive bodies, whereas all matter is essentially electrostatically held together because of the size of K. Now, here is the other bizarre nature of electricity compared to gravity. Gravity is only attractive. Only. Massive objects pull one another towards one another. No matter how small they are, as long as they have mass, they will have a gravity pull, and it is always attractive. Charges, on the other hand, can either attract or repel, and I believe your mom and them know that. There's a weird difference in the behavior of charge because it can come in two varieties: attractive force and repulsive force. So we're going to explore the nature of that idea by turning to this next slide. Gravity can only be attractive. Electric things can be attractive or repulsive. So we talked a little bit about the unit of charge before. We talked about it being derived from the SI units in a weird way. That's really not so important to us. Mostly what we said is that the electron has the elementary charge. Here's the charge, and I've shown you this number before. This is the charge on a single electron. Now, again, do I want you to memorize that number or anything like that? No. But what we will learn from looking at it is that it is tiny. The electron possesses a tiny amount of charge. And as far as we understand in the universe, this is the smallest amount of charge possible. There's no dividing the charge on an electron. It has this tiny amount, and if you cut an electron in half, you won't get half as much charge. Is that right? As far as we understand, you can't cut an electron in half either. It's a point in space. Don't get me started. It gets really bizarre out there when you start coming down to what is actually going on with electrons. They're essentially poking holes in space is what they're doing. It's kind of weird. Okay, so any larger charge is just done by adding electrons together. Now, because of the weirdness of the attraction and repulsion, we had to assign a sign to charge. So this has been assigned in order to help us determine which way the action of charge is. Now, that will come up on another slide here in a moment, and it has a little interesting story behind it. And just for your information as well, the person who was able to measure this tiny amount of charge on an electron, and it turns out to be the tiny amount of charge allowed in the universe, was this guy, Robert Millikan, who did so, as you can see, really not all that long ago. He probably measured this in 1930, something like that. Measured the charge, maybe in 1920. He measured how much charge was on an electron. Okay, now here is again where it gets really interesting. Because of the attractive or repulsive force that can be generated when charges interact, we had to deem them differently in some way to reflect that behavior. Again, reminding you, gravity is only attractive. All masses pull each other towards themselves, regardless of how much mass it is. Gravity is only attractive. Charges, on the other hand, are repulsive or attractive. So this person, who I'm sure we've all heard the name of, was the individual who deemed and first designated the distinct types of charges, and he decided that we should just call one positive and one negative. Now, the simple connotation I would imply to you for this designation is like this. If I have two charges, charge B is either going to be pulled towards charge A, or charge B is going to be pushed away from charge A. So it's either going to be pulled or pushed depending on the signs of the charge. So Franklin's idea essentially amounts to, look at a number scale now, and put 0 at the location of the charge itself. Then it can grow in magnitude in one direction if it's positive, and gets to be bigger and bigger negative in the other direction. So the positive or negative kind of reflects something to do with the direction of action that charge A will exert on charge B. So the idea of positive or negative is added by us to help us keep track of something to do with whether it's a push or a pull that they will exert upon one another. Now, again, let me return to the fact that these concepts which I'm discussing were introduced by Ben Franklin. Ben Franklin, ladies and gentlemen, is among the greatest Americans ever, and there's no doubt about that. Ben Franklin, I can't believe he wasn't president. There's many reasons why he wasn't president, but this is one of those being is that he thought politics was ridiculous, but he did get involved in it, of course, and he was one of the so-called founding fathers of the country, of course. But Ben Franklin had too many other important things to do than to mess around with stupid politics. What do I mean by that? If you have not looked into the life of Ben Franklin, he is a fascinating individual. And what I'm getting at with him is he was truly a Renaissance individual. Not only, of course, was he important in the politics of founding our country, signer of the Declaration of Independence, all those Continental Congress, all that stuff like that. Great. He was an inventor. He invented bifocal glasses that could help you see close and far away. He invented a certain stove that you could put into your house and it would radiate heat really effectively, called a Franklin stove, that you could build a wood fire in the stove. Instead of just you didn't need to have a fireplace, you could run a pipe out of your wall and put this radiative stove in your house, and it would heat your house up. He was an engineer. He was a philosopher. Every year he published the Poor Richard's Almanac, which predicted the weather and was pretty hokey. But it also had all these important statements he made about philosophies on life. I don't know if you've ever heard some of the quotes attributed to Ben Franklin, like a penny saved is a penny earned, and the only things that are certain are death and taxes, and just a whole bunch of other witticisms and philosophies that he came up with. But on top of all these other things, Ben Franklin was a fundamental scientist. I mean, like, I'm not talking about a pretend fooling around scientist. He was a scientist. He was working on electricity well before we understood anything about electricity. And he did fundamental experiments that even today we revere as being some of the most important work done in the early days of understanding charge. So, I mean, I'm going off on Ben here, but wow, just an incredible individual, incredible life story of the things he accomplished. Okay, so again, the basic idea that maybe we should take home from this is that there was positive and negative flavor associated with charge simply because of the fact that it is attractive or repulsive. You didn't need this in gravity. Gravity was only attractive, so you didn't need to have positive masses and negative masses. You only needed one flavor of mass, so all mass is positive. Whereas because of the attractive or repulsive nature of charge, we needed two kinds of charge. Okay, so we've talked about these things before. There's the charge on the electron. It's now designated as negative because of the way it is pushed or pulled by another charge, and it has this smallest amount of charge possible. Protons also carry the elementary charge, but protons have a different reaction than do electrons to that action, so it has positive, the smallest amount of charge possible in the universe. Again, these are things which we have discussed previously. I'm just reminding them here. Now, what do we do to charge an object? And I also mentioned this. Make sure we're clear on this. And as a matter of fact, I think I asked us something about this on our test 1 part 3 that we're already taking because we have discussed this concept before. Objects that are negatively charged do not become negatively charged in any other way by adding electrons onto them. And when you charge anything positively, since the protons are the positive charges, you would think that you're just going to add protons. No, they are buried in the nucleus, trapped in there in extremely crazy energetic states. Moving or adding or removing electrons from a nucleus is cataclysmic amounts of energy. It can be done, yes, but again, it is cataclysmic amounts of energy. In the typical energies that we deal with, where we charge or discharge objects, we only make things positive by removing electrons. We never make things positive by adding protons, period. So let's just look at a little numeric thing here again. Do not think I'm going to ask you to do something like this, but just suppose you wanted an object to have 1 coulomb of charge. Sounds like the smallest unit of charge that you could have in the SI world, one unit of it. How many electrons does it take? Well, each electron has 1.6 times 10 to the minus 19 charges. So if I do a little quick math, it would take 6.25 times 10 to the 18 electrons to acquire a coulomb of charge. Now, let me clue you. You easily can acquire a coulomb of charge in your bare socks, dragging your feet across the carpet, going towards the doorknob. So this is telling you something about the huge number of electrons that you're scraping loose from the carpet fibers when you're dragging your feet in your socks across them. Okay, so that, just in number terms, that is this many electrons you have to drag loose. Again, we aren't playing with the numbers here. I just wanted to show you the numbers. I mean, you won't be playing with the numbers. I'm showing you numbers just so you can get an idea of the kinds of things, the amount of entities we're dealing with. And also it should give you some feeling of how difficult it must have been to unravel this puzzle. To get even a small amount of this charge, you were dealing with huge numbers of these particles simultaneously. So the experiments that revealed all these ideas were very delicate, and it took a long time to really get concrete information from. Okay, so let's now do the same kind of thing that we did with pictures of the Earth and the Moon, but now let's do it with pictures of charge. So opposite charges exert attractive force on one another. So here I am showing you in red spheres, two oppositely charged objects. Now they will act on one another just like the sun and the earth, or just like the earth and the moon, or just like you and the earth. They will exert attractive force on one another. In many regards, it's just the same as the attractive force that the earth does pull on the moon with. I showed a cartoon earlier with pictures of the earth and the moon, and I had two arrows showing the direction of action of their attraction, and I'm showing very similar looking pictures right here. Now, what we should notice is, again, this is an example of Newton's third law of motion on the planet or on the universe. According to Newton's third law, for every action, there is equal and opposite reaction. So let's call the one on the left charge 1. We'll call the one on the right charge 2. So I could list something I called F12, which will be the force felt by 1 due to 2. I could list the number I call F21, which will be the force on charge 2 that is caused by the action of charge 1. F12 equals F21. They are the same in magnitude. Now, I don't care if Q1 is big and Q2 is tiny, or if Q2 is big and Q1 is tiny. Q1 pulls Q2 just as hard as Q2 pulls Q1. They pull on each other equal according to Newton's third law, but they pull on each other opposite, meaning the arrow from charge 1 points towards 2, the arrow from 2 points towards 1. So the direction of the actions are opposite one another. So the attractive force heads on the straight line to the middle of both charges. So you can just connect them with a straight line, and that's the line along which the charges act. Now, let's look at like charges. I can have two cases. I can have a plus to a plus or a minus to a minus. Now, for the moment, folks, let's pretend that the top two dots don't feel the bottom two, and the bottom two don't feel the top two, because, of course, there should be an attraction. Those are opposite charges, so the top dot should be pulled towards the bottom, and the bottom should be pulled towards the top. Let's pretend they don't feel each other. But the two pluses would act repulsively towards one another. The two minuses would act repulsively towards one another. Instead of pulling each other, they push each other. So I have push of equal magnitude. I don't care what Q1 is or Q2. If you put them in the formula, you just interchange the numbers. You take Q1 times Q2, then you take Q2 times Q1. Doesn't matter, you get the same value. So the magnitude of these pushes are the same. But according to Newton's third law, they are opposite in direction. Notice these arrows are pointing opposite of one another. One is heading to the left, while one is heading to the right. So Newton's third law of action-reaction holds for positive charges with negative charges, or for positive charges with positive, or for negative with negative. They all follow this idea. Okay, so the force, again, the directional, this acts, if you draw a connecting line between the two, then these would lie on an arrow right on that line. But now instead of pointing inwards towards one another, they're going to be pointing outwards away from one another. All right. Now, what happens if you have a whole bunch of charges? Now, here's what this cartoon is trying to show you. In space, I have a Q1. And in space, it is surrounded by three other charges, Q2, Q3, and Q4. And it says all these charges are positive. So all these charges are the same sign. So what I've drawn in red are the directions of repulsion that Q1 will feel. Now notice, I did not draw the repulsions that Q2 would feel. I did not draw the repulsions that Q3 would feel. I did not draw the repulsions that Q4 would feel. I could have done that. Since they're all the same sign, all charges are repelling each other. So they're all pushing against each other. But for simplicity and clarity, I'm only showing how Q1 is affected by charge 2, 3, or 4. Now, if I know the distances between them, and I know the magnitudes of the charges, then I could stick them into Coulomb's formula. F12, F12, I would put in Q1, Q2, divide by R squared, the distance between Q1 and Q2, and then I would multiply by K. That would give me a number F12. F13, the force that charge 1 feels due to 3, I put in the number Q1, Q3, measure the distance between them, divide by that number, multiply by K, I get a magic number F13. Likewise, F14, put in the numbers of charge of Q1, Q4, measure the distance that R is from between the two, divide by that squared, put in K, I get a number. We don't really care about the numbers. The arrows, though, represent the vectors of those repulsions. Okay? Notice they are all repulsions. Notice they all act on the straight line which connect the two individual charges. So there's a straight line connecting 1 to 2. Along that straight line, you push away charge 1 from charge 2. Draw a straight line connecting 1 to 3. Along that line, draw an arrow pushing charge 1 away from 3. And likewise, draw the straight line connecting 1 to 4. Draw an arrow pointing away from 1 along the line between 1 and 4. That's where I get those 3 red arrows. Now, guess what? Charge 1 is simultaneously being pushed away by 2, 3, and 4 along these 3 directions. Can I find the net or resultant push that charge 1 feels? And the answer is yes. What would I do? I would just take these individual lines. Oh, okay. First here I'm showing Q1 is actually pushing on everybody else. As a matter of fact, Q2 is pushing on everybody else. Q3 is pushing upon everyone else. But I'm focusing on Q1. All right? So I'm just showing you what Q1 will be doing on its neighbors with those arrows. But now, again, let's return to to force on 1. And there's 3 forces acting on 1. And I would like to know what the net force is. Well, we already saw what to do there. Take the individual arrows, lay them tip to tail, and then start from the last charge, start from the tail of the first charge that you laid end to end, and finish at the last charge that you laid end to end. So if I took the 3 arrows in red from the top picture emanating out of Q1 and connected them individually from tail to tip, tail to tip, tail to tip, and then drew the connecting line from that beginning tail to the ending tip, I would get a vector of length and direction that you see listed as Fnet. So Fnet has a combination of F14, F13, and F12, and you can notice Fnet is way longer than either F14, F13, or F12. That's telling you something about the magnitude of Fnet. Q1's getting pushed pretty hard, is what we're saying. And the direction that it's ending up being pushed is shown by the direction that Fnet is pointing in. Okay, so we can play the game of combinations of charges pushing on each other. We might do something like that, but again, no numbers involved, just summing up arrows, kind of as you're seeing in the pictures that you see on that particular slide. Now, let's talk on this slide. What I'm going to discuss with you is electrostatic attraction that you might experience. And you can do this little experiment at home. If you get something known as an amber rod, and what an amber rod is, it's really not made out. In the old days, they used amber rods. Nowadays, they use a plastic rod. What is an amber rod? It turns out amber is a form of sap which has been petrified over the millennia, and it forms a sort of a plastic that was used a long time ago. It's a nature plastic, if you like. It's a nature polymer. Further down later in time, we're going to spend a little time on plastic, and we're going to talk about the nature of the different forms of plastic, but we're not there yet at all. So when I say this name amber, it came from the sap of trees a long time ago, and it sat around in the atmosphere and in the earth for a long time, ended up into a material that is sort of a natural plastic-like material. It has the properties of being an insulator, as a matter of fact, and we're going to describe what that means in some upcoming slides here. But for the moment, let's just, for maybe a little more clarity of what we're going to do, if you don't like the word amber, just think of a plastic rod. So I have a plastic rod, and I put it near some scraps of paper sitting on the tabletop. There's no natural attraction that these scraps of paper would feel for this plastic rod that I'm putting in proximity to them. But now, if I do something weird, I take a piece of fur that has a lot of hair on it, and I start rubbing it up and down on the amber rod, or rubbing it up and down on the plastic rod. Same thing could be done with either one. Now, I put this by the scraps of paper that were originally laying on the table. Now, suddenly, the scraps of paper will be picked up by the rod, whereas before, they had no attraction to the rod. So something I have done by rubbing this rod with a fur strip has enabled the rod to be able to pick up scraps of paper. Now, you can do this same kind of experiments with paper clips. Put the paper clips down on the table, put the rod by it, nothing happens. Then rub the rod several times over with some fur or a piece of carpet even, whatever you want, then put it by the paper clips, and voila, the paper clips will be attracted and start to lift up off the table and stick to the rod. So the amber is, as we can now guess, we've talked about this a few times already, it is rubbing electrons loose from the fur. Just like you walking across the carpet, pick up a whole bunch of electrons on your body as you do so. While the fur gives up electrons, it is now positively charged. Okay, so the electrons leaving the fur make the fur positive. The electrons deposit on the rod, making the rod negative. And now what is happening when I take that away, the rod is negatively charged and now has the ability to attract the paper. The fur will be net positively charged as a result of that rubbing. Again, the same thing is true if you scrape your feet across the carpet will end up being positively charged. You will end up being negatively charged. But there's some, wait a minute. Something shouldn't make sense here. The second picture shows, or I'm sorry, the third picture on the left shows that after I transferred these electrons to the rod, it can now pick up the paper. Before I transferred the electrons to the rod, I couldn't pick up the paper, as the top picture on the left shows. And now on the right, I'm explaining, yeah, that's because the rod has been charged. But it doesn't explain a change in the paper. The paper I didn't rub the paper. I didn't do anything to the paper. So why is suddenly the paper attracted to the rod when the rod is charged, and it wasn't attracted to the rod when the rod is not charged? So how? That doesn't really satisfactorily explain the way the rod attracts the paper. But this slide does. There is polarization in the paper. Now, what does it mean that there is polarization in the paper? The paper is made up of charged entities. Of course, the paper is electrically neutral. But when you put charge near the paper, it starts to flip everything and line it all up. Inside the paper, if you put a positive charge near the paper, then inside the paper, the negatives which are attracted to that positive all kind of run towards the positive. The positives which are repelled from that incoming positive rod run away from the positive. So temporarily, the paper acquires a tilted, uneven charge distribution. Now, once again, if there's no charge near the paper scraps, the charges evenly distribute throughout the paper, and the charge is electrically neutral everywhere. When you put charge near the paper, it, as we says, polarizes, which means some of the scraps run, some of the positive charges, if I'm holding a positive charge towards the paper, run away. They don't like that. The negative charges in the paper run towards. They like that. So now there's an imbalance of charge in the paper, and it can stick to the rod. So if the rod gets polarized, it can if the paper gets polarized, it can temporarily attract. So that's the magic of the phenomenon. Now, if you don't like that, let me explain it in the same context, but now instead of using electrical attraction, let's use magnets. We've had a little more experience with magnetic attraction. In particular, let's think about sticking something on the fridge. If I just have a piece of paper and stick it up on the fridge, guess what? It falls off. Because there's no magnetic attraction between the fridge and the paper. But now I think we all know, if I put this paper against the fridge and stick a little refrigerator magnet on the paper, then it sticks on the fridge. Now, what is going on there? Is suddenly the fridge has become a magnet? It wasn't a magnet before. The fridge was not a magnet when I tried to put paper on it, but now it has become a magnet when I put another magnet on it. Okay, now let's get this straight too. If I just take a penny out of my pocket and try to stick it on the fridge, it doesn't work. So the fridge isn't a magnet to all metals. I take a spoon out of the drawer, hold it up on the fridge. Does it stick? No, falls right off. So any of these types of metal like that, the fridge doesn't act magnetic. But if I get a little refrigerator magnet that has a little stupid cartoon on it, or an advertisement for Morris Bart or something like that, it'll stick right on the fridge. How's that work? Suddenly, does the magnet know I should be magnet now, but I shouldn't be magnet later? The same thing is true on that fridge that I'm showing in this cartoon. Inside the material that makes the fridge up, there are a lot of individual magnets, but they're all oriented in all possible directions normally. So all the little atoms in the material have magnets in them, but they're randomly pointing up, down, left, right, sideways, diagonal, all possible orientations completely equally likely. So the fridge is not a magnet itself in general. But if I bring a magnet to the fridge, let's say I bring the north pole of a magnet towards the fridge, all the magic south poles that are in the fridge somewhere say, I like that, and they all run towards that magnet. The north poles that are in the fridge say, oh, we're repelled. They run away. So temporarily you are polarizing the fridge, enabling it to attract. If you take that magnet away, now all the internal magnets on the fridge all orient again randomly in all possible directions. So there's no net attraction of the atoms in the fridge after that random orientations reoccur. So the idea of polarization to temporarily make a substance attractive will work whether the substance is having electrical repulsions and attractions or magnetic repulsions or attractions. Okay, now this slide back here shows how we can make something negatively charged. So I can make an object negatively charged because electrons are easily rubbed loose from a material. So then how can I make something positively charged? It seems I can rub electrons loose from a material, and then what's left behind is positively charged. So I can make something negatively charged by rubbing electrons loose from it. Then the remaining material, as you can see on the right, is positively charged. Now, another trick that scientists use, I'm sorry, I thought I did that on this slide. I didn't do it yet. Let's first indicate something about conductors and insulators. A conductor of electricity is something that allows charge to move freely through it. So I think that should make sense to you. Anything that's going to conduct electricity is going to support the flow of charge. Anything that is an electrical conductor will be polarizable. It'll have this ability of charge to move through it so that it could be conducted if enough charge is moving through it. So conductors allow electrical charge to move through them. So what are some conductors? Well, we'll show on the next slide in our elements, but things like metals and iron, all that good stuff like that, those are good conductors. On the other hand, insulators don't allow charge to move freely through them. They kind of repel, or I don't want to use that word. They kind of, what's a good word? They kind of stop charges from moving. All the charges stay localized without migrating in a material known as an insulator. Now, what are some good insulators? Well, mostly plastics are good insulators. Not all, but mostly. Wood turns out to be a pretty good insulator as long as it doesn't have a lot of water in it. Air is a good insulator. Water, believe it or not, now that might seem contrary to what your mom and them would think. Water is really not a good conductor of electricity, but stuff dissolved in water is. Almost all the water you encounter has lots of ions in it, and that come from salt and other things. And those things are charged already, and they move really freely through the water. So the water molecules themselves are typically not good conductors of electricity, but everything dissolved in the water is. So that's where water generally gets its conductive properties, not from itself, but from the stuff that's already present in the water. So a general rule of thumb is that if you're a good conductor of heat, you're a good conductor of electricity. If you're a good insulator towards heat, you're a good insulator towards electricity. Now, does this apply in every case? Not really, but in most cases. Water is a good insulator towards heat. Water is a good insulator towards electricity. Rubber, plastic, wood, they don't get hot really quickly. That's why we put wooden handles on metal things, and plastic handles on metal things to keep the heat from transferring into that handle. And you try to pick it up with all that heat transferred into the handle. That don't feel good. So we make wooden handles on our pots and pans, and plastic handles on our pots and pans, because the heat doesn't transfer through them. Well, not only does heat not transfer through things like that, what I'm claiming here is neither does electricity as well. So those would be good conductors or insulators to both those things. Now here I'm showing you what we've already talked about with regard to the periodic table. Most of the elements in the table are metals. The metals are listed, and again, it's kind of covered up on the button below the slide there. But the metals are the elements that are in the purples and the magentas and the blues. And you should see it, essentially 2/3 of the table are in the purple, the magenta, and the blue. The lower left-hand side of the table, including everything at the bottom, is pretty much a metal. Now, the non-metals are the insulators. And believe me, this is one of the ways in which they establish which of these clubs you happen to be in. The non-metals are the elements in green. Now notice hydrogen is kind of an outlier. It's way on the left at the very top, but it's an element in green. And the elements in red, the elements in green and red and orange are what we will classify as the non-metals. The reason they're trying to put reds and oranges in there is they're also trying to show other properties in this table. So really the reds and oranges in this table should be green. So the greens are piled up with the reds and the orange in the upper right-hand corner of the table. Those are the regime where the non-metals live. Those are good insulators, poor conductors of electricity. Most of air is made of O and N. Most of air, and actually it's got CO2 and things like that in it too. These are all non-metals put together to make up the air. Air is a good insulator. Most of the plastics are made out of carbon, chains of carbon with hydrogen, and a few other dabblings of things. Most of the plastics are insulators. Wood is, of course, as you can imagine, made mostly of carbon and hydrogen, smattering of oxygen in there as well. These elements are non-metals. These elements are insulators. Wood is an insulator as well because of the stuff that it is made from. Of course, you can see in the middle of the table there, like iron and copper and things that are familiar to us that can conduct electricity and heat very effectively are in the middle of the table, and they are conductors. Okay, it looks like time is up for today. Please remember to complete your test 1, part 3, and until next time, peace out.